Welcome back. Our next speaker is Dr. Jim Chang, who joined TSMC in 2017. He currently heads the 3DIC Design Methodology Development Group. Dr. Chang brings over 20 years of semiconductor experience, specializing in synthesis, physical optimization, detailed routing, and timing analysis. Dr. Chang received his PhD in electrical and computer engineering from the University of California, Santa Barbara. So please welcome, once again, Dr. Jim Chang.
Good morning. Welcome to the 3DIC session. In the next 30 minutes, I'm going to introduce you our latest invention, the 3Dblox. 3Dblox is a groundbreaking way to organize your 3DIC data, and it is designed exclusively for 3DIC. So with 3Dblox, we like to unleash the ultimate 3DIC design productivities. So here's the outline of my talk. First, I will elaborate why do we do 3Dblox. It is the rising chiplet architecture's complexity that has motivated us to do 3Dblox. Then I will introduce the key definitions of 3Dblox, how it works, how it is designed. Then I will show the key productivity features we have put together for you, together with our EDA partners. Then I will highlight our key EDA collaboration milestones that we have collaborated with our EDA partners for the past full 1 year. And I will conclude with a summary. So let me start with our TSMC 3D fabric offerings. Start from the very left, we have a very successful CoWoS platform that has been used in many of the high-speed HPC applications. And from CoWoS, we have a new architecture we call CoWoS-R, which replaced the CoWoS silicon substrate interposer to use the info, our audio interposer, as the interposer type. Then it becomes CoWoS-R. Then from CoWoS-R, we created CoWoS-L, which the L stands for the local silicon interconnect. So inside the audio interposer, we are able to place silicon interposers that are selectively in the needed locations to provide even higher bandwidth using the silicon interconnects. And it's designed for very large chiplet with more than 10 reticle size. That is the goal. And on the info side, we have the very successful info pop offerings that has already been used in your cell phone applications, in many of the mobile applications. And from there, from info, we introduced info 2D. And then now we have info 3Ds. On the SOIC side, which is our front-end vertical stackings on system of integrated chips, we have the chip on wafer, the COW, and the WW offerings. So on the left-hand side, we have a lot of the 3DIC offerings, and it's growing. But on the right-hand side, we have a lot of selective offerings that can be used, mixed and matched into our 3D fabric offerings. And I can summarize them as the number of active dies. We can have 1 die, can have 2 dies, can have 3 dies at a particular layer. And we can have the passive device, choice of different passive device, like the deep trench capacitors and our enhanced deep trench capacitors, the integrated passive devices, and also our ICAP, which is the offerings in our CoWoS platform. And we also have various kinds of 2.5D, the horizontal interconnects. We have the silicon interposer, we have the RDL interposer. And on the vertical 3D connections, we have the typical TSV, the through silicon via. We have the TIV, the through info via. And we have the TMV, the through molding vias. And also we have various kind of interfaces. We have a system on integrated chip. We have the SOIC bond. We have the different size, various size of hybrid bond, bigger one or smaller ones. We have the BGA board, we have the C4, or we have our polymer via, which is our connection to info. So with the left-hand side and right-hand side, that can be mixed and matched. We have a lot of combinations. And this all tells us that our design complexity is rising in our 3D IC world. But now, when we look back in our current design ecosystem, and especially we want to look at how a 3D IC context is represented. And what we found is very interesting. Among different EDA vendors, there's a very much different kind of formats. For example, one of the vendors for their PDN analysis, they have a format. For APR, they have a format. Why is that? Because for the power analysis, the goal is to connect all the chiplets together and build a full IOC network. So the whole power distribution can be analyzed. But for place and route tool, the goal is to understand which chiplet is on top of the other, so the bindings can happen correctly. So there are two different formats, one for the logic connectivity, one for the physical connectivities. But there's not a single format that covers all. And each vendor has their own way to represent. So imagine you are a designer, you start from vendor A for the implementation, and you have to port everything you know about this 3D IC context into another vendor, maybe for sign-off, then maybe to another vendor for EMIR analysis, then eventually goes to another vendor for physical sign-off. And this is doable. This is doable, but it's very labor-intensive, and it's error-prone, and it doesn't really add any value to your 3D IC design. So we have an ecosystem that is very fragmented. That's what we see. So when we have a rise in design complexity and we have a fragmented ecosystem, what can we do? And we recognized that a year ago, about this time, last year, we set out to do something. We need to do something to make the 3D IC design easier. So what we set out as a mission statement is we want to find a way to modularize the design and the EDA tools to make 3D IC design flow simpler and efficient. And then we want to ensure a standardized EDA tools and design flows that are compliant to our TSMC 3D Fabric offerings. That was our mission statement. So now, let me introduce you what is the 3Dblox standard, and from our TSMC and our OIP partners. So starting from this rise in complexity, the thing is, if we want to manage complexity, we want to look at how the system can be modularized. What are the fundamental pieces of each 3D IC architectures? And can we extract them? So at TSMC, we started from the concept of modularization. But what we realized, modularization is a concept. And we cannot just ask our EDA partners to implement some concept in the air. So what we ended up with is a language, what we call the 3Dblox standard. It's a language we designed with modularization and generalization in mind. We designed this language. And when EDA companies, they implement this language, then they carry over this concept of modularization. So that's what we did. And on top of that, we realized our customer really want a top-down design methodology, meaning they can do this thing sequentially from a very vague description all the way down to a very concrete and tape-out situations. They can do this. So that's the top-down design methodology. And corresponding to that, we add what we so-called the assertions into this language. Then, on the bottom, we added this concept of chiplet reuse, because the nature of chiplet is they can be used in different configurations. And our customers are telling us they want this same implementation that can fit different configuration and it still work. So we add the concept of chiplet reuse and add it in with inside the language, it's the hierarchical instantiation. And also, as I have talked before, all these languages that is current in this ecosystem are nothing more than the physical connectivities and the logical connectivities. So we set out to design 3Dblox that covers both. So there's no other format needed in this industry. 3Dblox will cover them all. So this is a very high-level view of the 3Dblox. So from there, we start to look at our TSMC offerings. And you can imagine the whole 3D IC design is about designing the interface. So we first started from looking at all our possible interfaces, the audio silicon interfaces, the audio interfaces, and our bridge kind of interfaces. And we analyzed them and put them into a set of language construct. So when we design this construct, we do this in two kind of format. We do this physical construct, which capture the physical dimensions, their typical physical properties, and we design that into the language. Then, since it's all about interface, we explicitly design the connection construct that captures where these triplets are exactly connected. So with this set of generic representations, we can build a full 3D IC stacking, full representation with this kind of language syntax and semantics. And also we add the assertions that can continuously check your implementations to making sure certain property does exist. That's what we do as the 3Dblox standard. So take a deeper look into this language. So the language goes with the typical definition and the instantiation. So on the top, you see this chiplet definitions. From there, we first define what is a chiplet. And we define the corresponding regions that this chiplet can be interconnected to other chiplets. And out of this, since we already have the definition of chiplet and the interfaces, all the TSMC technology file can be automatically binded into these descriptions. So with that chiplet definition as a set of library components, we can instantiate them into a full 3D fabric representations. We got the chiplet can be multiply instantiated. And since each of the instantiated chiplet already have their interface defined, we create a set of we call the connectivity construct, or we call the connection object, that explicitly bind them. And with that, we will have a full representation of the physical and the logical connectivities. Then on top of that, we build the assertions. Well, we have the path assertion and the physical assertions. And together, it becomes the full context model for your 3D fabric designs. So here, let me use a CoWoS S structure, and step by step, we construct that with 3Dblox. First of all, you have the chiplet definitions. And in this case, we have a SoC die, we have HBM die, and we have the audio interposer. And each of them is represented by a set of 3Dblox syntax. And from there, we can instantiate those triplets. And you notice this SoC die is multiple instantiate twice. And then once they are instantiated, but they are not connected yet. But since we have all the interfaces defined clearly, we create 3 connection objects. And this connection object will explicitly bind those interfaces. And now they are fully binded. So with this information, we can actually build what we call the path assertions. And path assertions are connectivities that we know by design intention they should exist. Then 3Dblox implementation will follow these path assertions and make sure from top to bottom this assertion is respected. And now let's look at another example with the 3D Fabric CoWoS L structure. So look at this structure on the left. On the top, first level, we have 3 chiplets. And we are interconnected by 2 layers of infos in this green interposers. And embedded inside the info, we have 2 LSI die, the local silicon interconnect, which provides the needed bandwidth for connectivities. And we have the pure silicon one on the left, and there's a variation we call the LSI2, which has the silicon interposer also with a few layers of RDLs on top to provide a further bandwidth with a different RC perspective. So this is a very complicated structure. And with 3Dblox, since we define those connection objects, explicitly combine them. With this information, we are able to build what we call the transitive connectivities, which means because our connection objects are essentially one-to-one mappings. They define the A connects to B and B connects to C. And with transitivities, we know A connects to C. So we can essentially, just simply based on the language model, we can build the full stack connectivity model. And this will be essential for our path assertions that works on this generic graph. So next, let me introduce those key productivity features that based on the 3Dblox language, what can we do with this? First of all, remember we said that we want to design the language with the top-down design methodology, meaning we want this design to be correct by constructions. So we built into this language a 3 abstraction level, starting from the black box level, where you only have a basic contour of the chiplet. And just by placing this very rough models, there's already a lot of design rules that can be checked. For example, the chiplet spacing, chiplet enclosures, or number of chiplets that are available in this our design rule, based on our design rules. And we can already place path assertions on this very simple model. And then in the left F stage, where the design is really Pearson routed, we can find the right locations because 3Dblox defines exactly where this interface happens. It can automatically help you to call the corresponding interface LVS deck to check the interface LVS. And it also can check the path assertions carried over from the black box stage. Then finally, when we go to the GDS stage, where everything is fully implemented, 3Dblox allows you to call the corresponding DRC LVS stacks at their particular locations. And on the assertions, I already discussed the path assertions where we explicitly want to find the path that exists between certain chiplets and want that property to be maintained throughout your design cycle. And on the physical assertions, this is a top view of a few chiplets, one on top of the other, under a big interposer. So even with these contours, we have enabled EDA companies to just based on this simple model, they will be able to write out a very simple GDS that allows us to use the GDS against our DRC deck to make sure all your top-level placement of the chiplet is correct by construction. The next thing is about the interposer hierarchy auto creations. In 3Dblox, the language itself will make sure it has strong one-to-one mapping between the 3Dblox names to our top-level Verilog. So take this as an example. Look at the upper left one. We have a top-level Verilog with 2 modules, and each of the module represents a chiplet. And in the corresponding 3Dblox view, we define 2 chiplets on top of silicon interposer. So it is important that we maintain the mappings between 3Dblox and the Verilog, so the EDA tool can automatically deduce a feed-through hierarchy for this Verilog. And why do we need that additional hierarchies? Because it maintains a one-to-one mapping to our 3Dblox model. And the whole point is we want to implement this interposer by itself, which means we need a clear definition of the input and output, which can come from this Verilog. And then we want this chiplet, the interposer, to be verified by formal or by LVS. And this also needs the Verilog Golden. So it's important that we need to get this feed-through hierarchy generated. But it's actually very elaborated, like if you want to generate this by yourself manually, and it's an error-prone process. So we enable the EDA tool to automatically generate this for you. And with that generated Verilog hierarchy, we can do further automations. For example, if you look at the bottom ones, this Verilog hierarchy can automatically generate into Allegro, Cadence Allegro format. We call the MCM format. And that captures all the bump locations and the inherent netlist connectivities. And together with the TSMC infotech file that we captured from our design rule to a set of language construct, that the tool will automatically be able to generate the auto-routing result for your info implementations. And the same is true for the silicon interposer. The Verilog hierarchy can be used to combine it with our APR tech file with the initial floor plan creations. It will be able to perform the silicon interposer routing. So that's a lot of productivity helps based on 3Dblox. So with one format that can be used throughout the design cycle, you can see 3Dblox can be used in many of the applications. For example, the power analysis applications for STA, for DRC LVS, or thermal analysis. So let's take thermal analysis as an example. If you do the thermal simulation model, what you will find is it takes a lot of scriptings just to simply describe stacking structures and the connectivities and also the bindings to TSMC thermal tech file with all the material information, thermal conductivities. It's difficult. You have to write hundreds, if not thousands of lines of code. And for each vendor, if you want to switch vendors, you will do this again and again. So with 3Dblox, you just take this with one line of code, importing the 3Dblox model, importing the TSMC thermal tech file. We make sure the thermal tech file works 100% with 3Dblox. And immediately you get the simulation model. So with this, since all the tools are now speaking the same language, I'm sure you can see this allows all the EDA tools among all the EDA vendors, they all speak the same 3Dblox language. And we create an ecosystem of very high interoperabilities. So on top of this, TSMC has decided to provide what we call the 3Dblox design template. So these are a set of templates that TSMC has pre-configured, pre-qualified, that you can directly use based on 3Dblox. So imagine you have an architecture, for example, on the left. This is the SOIC structures with 2 top dies and 1 bottom die and 2 HBM dies on top of a silicon interposer. You can imagine how many tech files are there. There are at least 50 different tech files. For each chiplet, It can be an N3 technology, can be an M4, can be an M5 technology, or maybe N65. And each of them has APR tech file, DRC, LVS. They have all kinds of mapping files from APR maps to DRC, GDS, from GDS map to RC tech file, or thermal tech file, or info tech file. There's more than 50 of them. And currently, without using 3Dblox, they're gonna be delivered as a bundle. And our customers would have to make sure they are using the right thing for their right purpose. But with 3Dblox, since we already have for a particular architecture, that chiplet has already been defined clearly, the interface defined clearly. We pre-bind all the TSMC tech files such that it can be used directly. And we make sure all our offerings, we have this kind of design template. And what can you do with this template? Well, in the flow, for example, in the bottom path where I label this non-3Dblox flow, you would have to create this yourself with all different EDA tools. Each of them you have to specify. You have to define the chiplet, define the stacking, define the LVS, DRC, where it should be used. Easily thousands of lines of code. But with 3Dblox, it's just one line. You import this database, you import this 3Dblox format, and boom, it's there ready for you. You can further elaborate, you can further manipulate, and you can save back to another 3Dblox file. And also, we provide you all the assertions that we can think of, and this will provide a second boost for your downstream further optimizations. Okay, now let's look at the collaboration milestones. So we started last year, and at the January end of this year, we started to push out the 0.1 versions. And with EDAs, we worked together for 2 months and come to the 0.5 version. And then we work for the full half a year and get everything implemented. I'm sure you can see that 3Dblox has unified and fundamentally changed the 3D IC design ecosystem. And here's another readiness. The features I talk about has all been listed here. And notice the first one, the design template, has all been supported from all the 4 major EDA vendors, and interoperabilities that we strive hard to maintain throughout the ecosystem. And also, we create 5 test cases of different complexities and drive all the EDA vendors to work with on various architectures from CoWoS to CoWoS-L, Info 3D, SOIC. We make sure everything is ready. All right, now let me come to a summary. So the future of 3D IC design has arrived. In the past 30 minutes, I've shown you our latest inventions on 3Dblox. It has been fully validated across all the EDA vendors and tested by our TSMC test chip. And if I can summarize with only one sentence, 3Dblox is one data format that unifies 3D IC logical connectivity and the physical connectivities, and leading to a significantly simplified design flow. And also, but this cannot be done without the collaboration with our EDA partners. So I want to take this opportunity to thank our partners, the Cadence, Synopsys, Ansys, and Siemens, for sharing the same view and goal with us, and worked very hard for the past 1 year to make 3Dblox possible. So after my presentations, we have put a strong lineup of 4 additional technical sessions, and each of the EDA vendors will further elaborate on their views of 3Dblox. I highly suggest you to attend those sessions. So with 3Dblox, we will unleash your ultimate 3D IC design productivities. And this concludes my talk. Thanks for your attention.